Everyone, looking at class number 31. Today we're going to talk a little bit about apparent weight. So this is one of those situations where normal force and force of gravity are actually not equal to each other, because this is where an object may be accelerating upward or accelerating downward. All right, so one of the things we spoke about was to think about if you're on an elevator, like the Tower of Terror, and the cable is cut. Okay, what happens to you in the elevator? And if you were standing on a scale, what would the scale read? So if you were on an elevator standing on a scale and the cable were cut, you would free fall, right? You would fall. The elevator would fall at 9.8 meters per second squared. You would fall at 9.8 meters per second squared. That would be your acceleration. That's how quickly you're speeding up each second. The scale that you're standing on would read 0. We're going to solve for that in a little bit, but the scale you're on will actually read 0. You are in a state of quote unquote weightlessness, as people say. Not that you don't have weight, but you're apparently weightless. Now, on the International Space Station, our question was, why are you floating if you're on the International Space Station? A lot of you said there's no gravity in space. There's less gravity in space. Now, if you're in deep space, far from anything, like really far from anything, then yeah, there'd be very little to no gravity. But the International Space Station is very close to the Earth, actually. If you think about the moon, what keeps the moon in orbit around the Earth? It's gravity, right? So there's got to be gravity in space. Again, unless you're really far away. So the International Space Station is only like a few hundred kilometers up in the air. So why are they floating? Well, what's happening is, and this is the scenario we spoke about, the International Space Station. Think about a cannonball on Earth. If you have the cannon up really high, like on a gigantic mountain, and you fire a cannonball really fast, as the cannonball falls, like any object will fall if you throw it or fire it, if you do it fast enough at a high enough altitude, the curvature of the Earth will match, excuse me, the trajectory of the ball will match the curvature of the Earth. Okay, that's what orbit is. So the people in the International Space Station are actually in a perpetual state of free fall. They're falling towards Earth, but since they're going so fast sideways, as they fall down towards Earth, the curvature of the Earth actually kind of quote unquote curves away from them. All right, the surface of the Earth curves away from them. All right, so it's a very precise science to get things into orbit around the Earth. You have to have a specific altitude and velocity, but once you get those down, you can maintain an orbit around the Earth. So how are these two situations different? The cable being cut on the elevator and a person on the International Space Station. In both cases, the astronauts and the people on the elevator are in a state of free fall. Okay, and we say they are weightless. Okay, not that they don't have weight; they totally have weight. All right, they definitely have a weight. That's a force of gravity acting on them. It's just that they're apparently weightless. So let's think about some elevator scenarios here. It says, have you ever noticed on an elevator when you get to your floor, sometimes you feel a little bit heavier or lighter? This is because your apparent weight is changing. So we looked at 4 scenarios and looked at how your apparent weight changes. So if the elevator accelerates upward, you feel heavier. If the elevator slows down while moving upward, you feel lighter. If the elevator accelerates downward, you feel lighter. And if the elevator slows down while moving downward, you feel a little bit heavier. And if the scale is in free fall, if you're in free fall, the scale will read 0. This is known as weightlessness, not because you're actually weightless, but because you're apparently weightless. Okay. Now you can actually answer numbers 1 through 4 using the idea of inertia, that an object does not want to change its state of motion. For example, why are you apparently heavier as an elevator accelerates upward? Well, you want to stay, if you're stationary, you want to stay stationary, right? If the elevator starts moving upward, your body for a moment while you're accelerating wants to kind of stay where it was. Okay, so you're kind of almost get pressed into the ground a little bit. Then once you reach a constant velocity, then you'll feel the same weight again. Your apparent weight will return to your normal weight. Notice how 1 through 4 all require acceleration. I am not saying moving upward and moving downward simply change your apparent weight. You have to be accelerating up or down. All right. So let's look at this question here. This is 4 scenarios of a person on an elevator. So the person has a weight of 700 newtons. What is his mass? Fg equals mg. 700 equals m times 9.8 because we're on Earth. That's why we use 9.8. So we get that the person has a mass of 71.4 kilograms. We're going to use that in this one here. All right. So let's go through this real quick. I'm going to draw the free body diagrams in each of these scenarios. So the first scenario is when there's no acceleration, but I'm just going to go strictly by the scale readings. So first thing, we have a force of 700 newtons going down. That's the weight. And going up, we have 700 newtons. That's the force of the scale. That's the scale reading. Okay, those are our only two forces acting on the object. The scale reading is the upward force acting on the man. Right, so we're going to use the equation A equals F net over M. A equals 700 plus negative 700, that's a bad 7, all over 71.4. I should put the units in, but I left them out for now because the answer does come out to be 0. All right, so constant velocity, when there's no acceleration, the scale reading is equal to your weight. Now again, constant velocity, you can be moving up or down with constant velocity. You can also be stationary because that's constant velocity too, constantly 0. All right, so let's check out this next one here. All right, first one, we have 1,000 newtons going up. That's the scale reading, so that's how much force the scale applies on you. And your weight is still negative 700 newtons. Okay, negative because it's pointing down. So we're going to say A equals F net over M. A equals 1,000 minus or plus a negative 700 over 71.4. And we get an acceleration of 4.2 meters per second squared, positive. So you have to be accelerating upward here. The next one, the scale reading was 400 upward. Weight doesn't change. That's still negative 700 downward. A equals F net over M. A equals 400 plus a negative 700 all over 71.4. And the acceleration goes to be negative 4.2 meters per second squared. So when you accelerate down, it looks like you're a little bit lighter. That's what the negative is, downward. And the last one is free fall. Now we know the acceleration should be 9.8, but let's prove it. So we have negative 700 here. And we actually, upward, we have a force of 0 newtons. Okay, there is no scale reading. So we're actually going to just leave that blank. Okay, don't even put a force there. So A equals F net over M. A equals negative 700 newtons over 71.4 kilograms. So A equals negative 9.8 meters per second squared. So you're accelerating downward. So accelerating upward or decelerating downward, when you have a positive acceleration, your apparent weight is heavier. You can say greater if you want. This is the same as scenario B, the second one. Accelerating downward or decelerating upward makes your apparent weight lighter. That's the same as scenario C. Moving upward or moving downward with a constant velocity, okay, that's when the acceleration is 0, so that's scenario A. Again, you're not accelerating, so you have the same weight. And scenario D above is known as weightlessness. Weightlessness. That's when you and your surroundings have the same acceleration. All right, a student is standing on an elevator that travels from the first floor to the 10th floor of a building. The student exerts the greatest force on the floor of the elevator when the elevator is. So think about this. We've been talking a lot about the force of the elevator on the student, the force of the scale. So when the student exerts the greatest force on the floor exerts the greatest force on the student. So basically, you're looking for the greatest scale reading. That's when you accelerate upward. All right, folks, so there it is. If you have any questions, let me know. If not, have a wonderful day.